Hello Year 10. This week's first job is to annotate this diagram. Okay, I've given you some clues about what the diagram's about. I've got the start of the title, EM something. I've got some labels in here. I've got this little cartoon that maybe will be able to help you with a really important word. But I want you to find a song like I did before, 4 or 5 minutes long, maybe 6 minutes long. Choose as a timer to annotate this diagram. So find that song and pause this video now. Okay, so hopefully you have annotated your diagram now. If you haven't, that's what you need to do. The title was the EM spectrum. Okay, if you don't know the order, you need to listen to the song in the video's description. We've got these little cartoons here. We've got a cartoon iron on its eyes, iron, eyes. And this is a crown, kings wear crown with no K, ing, ionizing. Ionizing. So some of my notes, we've got UV, X-ray, gamma rays are ionizing. They can cause cancer. We've got wavelength going up in this direction. We've got energy going up in the other direction. I've got some dangers and some uses. More uses and more dangers would be really good to see. Maybe having an arrow that shows frequency increasing opposite to the wavelength. So this would be high frequency. This would be low frequency. I've got the rainbow section colour expanded up. We've got visible light. Okay, you need to be aware of these numbers. You need to know these kind of powers, and you need to know the order and wavelength, the order and energy, and the order and frequency. Okay, you need the uses and dangers of every different section. Okay, so take a picture of that, take a picture of what you got, and you can upload that with the rest of this week's work. Now, last week you uploaded some absolutely brilliant stuff. Here we've got a really good description about fuses in the earth wire. Really goes. The thing that I really liked about it is it really emphasised the fact that it's fuses in the earth wire is reducing the chance of getting fires. It's not that it will stop you getting electrocuted. Okay, that will stop that happening in the long term because it will stop working. But it's really designed to stop fires from happening. Okay, and then some really nice diagrams showing plugs and some uses of the different parts of it. I'm not sure what's happening here. I'm not sure why that's not been clicked. But there we go. But on the whole, the work that's been uploaded has been absolutely brilliant. Okay, so well done, Year 10. This week, we're looking at power and energy transfer. Okay, it's got massive links with the energy topic, really strong links with the energy topic. AQA boards, they really, on the whole, they like to link all of our little topics to that energy unit, most of all. Okay, so there's a big link between electricity and energy, and this is one of the places where it happens. So your first job, I've got these 4 equations. You need to know these units, you need to know these symbols, you need to know these equations. So your first job, I want you to write these down, and I want you to try and figure out what each of these letters might mean. If you're not sure, that's okay, but I want you to give it a go. Okay, what are the symbols? What are the units? So pause the video and give that a go. Maybe spend a minute. Okay, so next slide, I've got what they are. So you need to check your work. So we've got E for energy, joules, P for power, watts, T for time, seconds. Okay, we've got power is watts, potential difference is volts, current is amps. We've got power is watts, current is amps, resistance is ohms, energy is joules, Q is charge, which is coulombs, and potential difference is volts. Now the letters here are confusing. They are confusing. Your teachers, we get that. Okay, why would you call charge a Q and label it with a C? Okay, over the last couple of 100 years, they've run out of letters for equations, and they try and make it as least confusing as possible in the long term. For things like, well, why couldn't we use a C for charge? Well, current's also a C, and then why can't we have to use like an A for that? And it's in amperes. A French guy found it. So there's lots of reasons for each of these letters, and the long and short of it is you need to know them. This is what they are. This is what they'll be given to you in your exam. You need to know them. Okay, so you need to know what these are, learn them, learn the units. One last thing, J's, there should be a capital. It's not a great font. It should be a really clear capital with the line across the top. Okay, it's a name. Right, next, we're going to go through each of these equations in turn. So first one, we've got energy equals power times by time. The total energy used is equal to the power of the appliance multiplied for how long, not ling, how long it is on for. Okay, so if I've got an appliance that uses some kind of power, and I use it for some length of time, if I times those things together, I get the energy used. So if I have something that uses more power, so if I have like a little handheld fan that doesn't use much power at all, it might use a watt, maybe 2 watts. Or if I use a big electric kettle, that might use 1,000 or 2,000 watts. Okay, the bigger the power, the more total energy is going to be used. Okay, likewise, if I use something for longer, the total energy will be greater. Okay, it'll be using that power for longer. So my first little question here, how much energy is used for an electric kettle at 2.5 kilowatts for 5 minutes? I want you to have a look at that question, and pause the video here and just scribble down an answer. Okay, how would you do it? Don't be tricked. Okay, so pause the video, give it a go. Right, the trick is 2.5 kilowatts. You've got to convert the units. 5 minutes, got to work in seconds. You've got to change those units. So 2.5 kilowatts is 2,500 watts. The time is 5 minutes or 200 seconds. Okay, and then we just times those two things together. 2,500 multiplied by 200 to give me 750,000 joules. Next equation. This one conceptually is tough, I think. We've got energy equals Q times V. And I've got this little circuit diagram here as well. The energy transferred to an appliance, to something in my circuit, is the amount of charge that goes through that component multiplied by how much energy each of those charges has. Okay, and how much energy each charge has is really the potential difference. So if I've got this circuit here, each of these electrons is holding 3 bits of energy. Okay, and to get the total energy going into that lamp, I need to know how much energy each of those electrons has, the 3, multiplied by how many will go in total. Okay, so if I know how much energy each has and how many charges go through it, then I can find out the total energy. Okay, energy equals charge times by voltage. So if I've got an electric toothbrush, it uses 3 volts. Okay, and it's got a 140 coulombs that passes through it. To find out the total energy, I just times those two things together. Okay, I have the charge of 140 times by 3 volts to get me 420 joules. Okay, nice simple calculation. Conceptually, I think this equation is really, really tough, but in terms of your exam practice, they'll give you easy examples. Okay, most of the time. Okay, it's just substituting in the equation. Okay, figuring out what's the important numbers and putting it in. The next 2 equations, you don't get examined on where they come from, which I think is a little bit disappointing, to be honest. You don't really have to know, and they're just plucked out of the air to a certain extent. You can derive them, you can figure them out using energy equals power times by time and Ohm's law, V equals IR. But you don't have to do that. It's an A-level question. Okay, but you do need to know these equations and use and apply them. So if we've got this first example, the power input of a light draws 0.2 amps of current from a 230 supply. How do I find the power? I just put the numbers in the equation. I just put in 230 as my volts. Okay, my potential difference times by my 0.2 amps, my current, times 2 together, get 46 watts. Okay, just simple substitution. The next one is a little bit more tricksy. This one, I've got a motor, and it's got an internal resistance of 25 ohms and operating power of 64 watts. I need to find the current it draws from the battery. This I need to rearrange. So I know that P equals I squared R. I rearrange I equals the square root of P divided by R. I put those numbers in. I get the square root of 64 divided by 25, which equals 1.6 amps. Okay. Now, this week's work, okay, we've got 2 sections. We've got these practice recall questions. Okay, they're going to be attached in your classwork's homework, as well as left in this video here. You need to answer these questions and answer the application questions. We're spending maybe an hour on this work, so if you get to the point where you've spent a lot of time, stop there and say, I spent this amount of time next to question 3 and this is where I got to, something like that. Don't feel like you have to spend hours and hours and hours if you're finding these questions really tough, because some of them are pretty difficult. Okay, so do what you can. So, I hope you have a brilliant week this week. Well done for all your hard work, continuing, and take care of yourselves, take care of your family. Bye-bye.